Swayam Prabha. Digital India. Educated India.
Good morning, welcome to the NPTEL lecture on architectural acoustics. We are in the 7th week, lecture number 32, and this lecture is on the airborne sound transmission too. So, it is the subsequent lecture which has been delivered on the transmission on airborne sound transmission 1. So, the learning objective of this particular lecture is, the first one is we will discuss the noise criteria curve. This is one of the very important criteria curve for noise potential point of view, and how this criteria curve is helping for designing my transmission loss also. And we will try to differentiate between the transmission loss and the noise reduction, which is again there is a slight difference between that, and we will try to find out what is the difference between transmission loss. Already we have covered in the last lecture, if you remember. So, the noise criteria, see, noise criteria is again a number and a curve, a set of curve which is having a numerical kind of index number, and which is actually created for a different sound pressure level and corresponding to different octave band frequency. It is very similar to the loudness contour curve, but there is a significant difference to for this noise criteria and the loudness curve. The goal for the the noise criteria curve is that it is related to a particular activity space. So, is some activity may required or may not required a particular higher level of the background sound or background noise. Some activity may allow that particular amount of the background noise sound. So, what should be the criteria for this noise, or the criteria for the background noise is actually expressed by some family of curve, and that is nothing but the noise criteria curve. So, why this background noise is disturbing or undesirable? There are many reasons. Out of those many reasons, one is it create the fatigue. It create fatigue to the people who are actually in the noise sensitive zone. It will reduce the productivity of any sort of its productivity, not only the productivity of the industry, it may be the productivity of individual, when suppose you are typing or when you are actually reading some books. So, you are acquiring some kind of the knowledge, or you are doing some kind of the official job. So, everything can be translated in terms of productivity. So, it can be reduced, that productivities also. Health and safety, if you are under a certain amount of background noise always, there is a problem if your health and safety is also. And the ability of communicate. So, if there is a background, if there is the background the noise is too high, or maybe above some cutoff level. So, the ability of communicate, the speech or any kind of a music will be a problem. So, that is why fundamentally a set of curve is generated based on this OBCF, the octave band central frequency, from 63 to 800 in x axis, and the SPL levels in the y axis. Please remember, in the x axis this OBCF are in logarithmic scale, and the set of curve is described or found out, and this set of curve are numbered as NC, noise criteria, from 15, 20, 25 like that to 65 or maybe some 1 or 2 above. So, out of this knowledge, the NC curve, the NC 65 and 60, these two are called as the very noisy. So, if those curves based on the frequency and the SPL level are treated as a very noisy kind of a background noise or background sound. So, if you found a particular receiving room, a room is having that particular curve, your the frequency and the SPL level is around like this, the top red line. So, it is under the NC 65. The noisy is 55 and 50, moderately noisy is NC 45 and 40, the quiet is 35 to 30 and like that, and very quiet is 25, 20 and 15. So, now the recommended noise criteria for any spaces is something like that. Suppose you are in a recording studio. So, this is a particular recording studio in IIT Kanpur, where I am recording the sound for this NPTEL course. The noise criteria should be very low, it should be NC 15 to NC 20. So, something like here. So, any background noise should not be more than this particular level. So, if it is some bedrooms, residential bedroom, hospital, apartment, hotels, so it is little bit higher, but still it is 20 to 30. So, auditorium, theatre is 20 to 30 again, the private office, conference room, library, etc. is 30 to 35. So, office, receptions, etc., gymnasium, restaurants is bit of noisy, which is 35 to 40. The laboratory, workshop, corridor, any building corridor or any equipment room is 40 to 45. The kitchen, laundry, industrial shop, machine room is 45 to 55. Those are the specific recommended noise criteria for any space. But this noise criteria, as you know, this is a curvilinear line. So, it may have different SPL value for different the frequency. So, there may be equivalent dB for all those. So, it is almost like if it is NC 15 to 20, it is almost about 25 to 30. So, there is a little shift from the NC to the NC, the actual equivalent dB. So, this noise criteria curve is described in various countries in various ways. This noise criteria, what is it can be, there are various countries recommend various type of curve. It is sometimes called as a noise rating curve in UK. The PNC, the preferred noise criteria curve, also it is called as sometimes room criteria curves. But out of this noise criteria or the NC is widely used and accepted. It is almost virtually the same, slight difference or slight parametric difference are noticed between these all four. And the NC was actually developed in the ASTM, that is the American Society for Testing and Material. They have developed this particular NC curve. So, again I have sketch that particular source and receiving room in a section, and there is a vibrating machine and there is a noise sensitive zone. Somebody is actually studying next to that particular vibrating machine zone or so. So, there is a noise level, there is a noise level in the source room, because of this particular machine is creating some kind of a level of noise which is equal to Ls, and there is a permissible background noise level criteria for study. So, with respect to this NC curve, NC 30 or 35 or so, and equivalent the dB level also. So, the noise transmitted from the source room to this receiving room, and I have shown that in this green dotted line, which is a transmitted noise or noise level or LR in the from the source room, which is comes to the receiving room. Now, this much, this red line to this dotted lower the horizontal portion of the green line is the noise reduction. This is the typically noise reduction between the source room to the receiving room. Now, the next is that this noise reduction can have, I mean from the designer point of view, there are two options or the two possibilities. One, this noise reduction is very less. So, this dotted green line is floating above the blue line. What is the blue line? The blue line is the permissible. So, the noise which comes from the source room, due to the very weak or faulty partition wall, the noise level in the receiving room is almost same or little the deviation, little reduction, and so this particular room is now badly affected because the permissibility is above the noise level is above the permissible noise level as per the NC curve. So, it is not desirable. Whereas, if this green dotted line, which is the noise level transmitted from the source room, is synced down from this blue line, which is the actual background noise criteria, it is acceptable. And you see the noise reduction NR is very high with compared to that. Then I can say this particular wall behaving excellent, because it is transmitting, it is not transmitting that much of the noise, and the transmission loss is very high. So, this criteria is favorable, desirable for any kind of a designer. So, let us see another way. This is a source room and a receiving room, and there is a noise source of which is gives me IS. IS is the intensity of the sound in the source room, and this is the level of the sound is in the source room, and there is a partition wall. And suppose the partition wall, the surface area, exposed surface area in the receiving source room is S. So, I can say that the sound power which is actually striking to that particular exposed partition wall area is nothing but IS into S. Why? IS is the intensity watt per meter square multiplied by the total area, exposed area meter square. So, I can find out what is the sound power, that is Ws. And this particular amount of sound power, which is Ws, is striking in the source room, is now try to travel to the receiving room by virtue of some vibration, creating some vibration or in that the partition wall. Now, in the next there are LR, I mean this LS now is going down to LR, and this decrease in this level is your TL, or this particular noise reductions or so. Now, this LR is how to find out this LR, or how to find out the sound power level in the particular the receiving room. The sound power level in the receiving room, I am interested because I can find out the tau for this particular this 2. Tau is the sound the transmission coefficient. The sound power is nothing but the sound intensity available in the receiving room. Of course, it is the average intensity, which is IR, which is again watt per meter square multiplied by the total absorption in Sabin or meter square Sabin. So, this is my assumption is that the sound intensity available in the receiving room, which is IR, is actually eaten away or taken away by all the sound total absorption in the receiving room. So, if I multiply this two the sound intensity in the receiving room by the total absorption, I can find out the wattage or the sound power level at the in this particular the total absorption of the sound, that much amount of sound is the surface area and multiplied by the respective alpha value. So, I can say that WR, which is the sound power level in the receiving room, is nothing but this IR, the intensity in the receiving room multiplied into A into alpha. Now, I have these two quantity ready for me. One is Ws, the sound sound power at in the source, and the sound power at the receiving room. So, I can now find out what is the value of the tau. Tau is nothing but, if you remember in the last lecture we have discussed the ratio of WR and Ws, the sound power in receiving room by the sound power in the source room. So, you can express the sound power in the receiving room by IR into A into alpha, and sound power in the source room is IS into S. S is the surface area of the exposed surface area of the wall, partition wall. And now, if you just rewrite this equation, and by definition, as you know, the TL is 10 log 1 upon tau. So, this 1 upon tau is placed over here, and then again this 1 upon, so TL becomes this and now you separate out this I s and I r with a logarithmic term, and this s by a alpha in other logarithmic term because it is multiplication, and this log 10 log I s by I r can be rewrite in this format of the level of the sound format, where I s by I reference logarithmic of that into 10 is nothing but your the L s, and this is I r by I reference logarithmic of that into 10 is nothing but your L r, and this will remain as 10 log A alpha by S, and then again I can rewrite is that this is L s minus L r equal to T L plus 10 log A alpha by S, and finally I can rewrite this as a equation like the noise reduction is transmission loss plus something plus log of A alpha by S. Now, this transmission loss, if you see, the noise reduction is, if it is the difference between this, is actually having two component. One is the transmission, pure transmission loss of the partition wall, which is maybe the maximum, and another small part which is the quality of the receiving room, that gives you, plus the surface absorption or the surface area of the exposed surface area of the partition wall, it gives you the slight reduction also. So, as this plus this. So, the noise reduction and the transmission loss are not same. Noise reduction is definitely little higher than the transmission loss of the any partition wall, and it can be expressed like this with this equation. So, let us have a small problem and let us solve the problem. The noise level in source room is 70 dB, and this partition wall, I have a partition wall having a window also in that wall. The area of the wall is 32 meter square, having TL of 30 dB, and the window of the area of there is a window also, and that area is that area is 8 meter square of TL equal to 40 dB, and there is a in the receiving room side, the size of the room is 10 meter by 7 meter, and the 4 meter is the height, and I have written down all the alpha values of the wall, ceiling and the floor. So, my job is to, or the fundamentally I want that what will be the sound pressure, sound level in the receiving room or the LR. So, here as I did it in the last lecture, I translate this TL to the taus of wall or window. This 30 dB gives me 10 to the power minus 3, this 40 dB gives me 10 to the power minus 4, and I calculated the average based on the individual area and the total area, and then finally the average, the sound TL average of this partition wall was found as almost 31 dB. Now, this is the TL of the wall, but that is not the total sound reduction. So, you have to find out the sound environment in this receiving room and the total absorption also. So, for that the wall area I have found out, I found out the ceiling area, I found out the flooring also, how much is the flooring area, and corresponding those alpha values of those area, multiply that gives me the A alpha. So, the total sum of the A alpha of the receiving room is 114.9, almost about 115 meter square 7. So, now I know this is the reduction or the noise reduction and the sound reduction from L s to L r. I know this L s is my 70 dB. I know this TL is 31, and this 10 log A alpha is 114.9 as I computed in the last slide, and this 40 is nothing but the total surface area S of this particular wall, because this is length of the wall is 10 meter and the height of the wall is, if you take as a 40 or whatever, is 40. So, now if operate this, you can find out finally the LR, that is the sound level in the receiving room is 34.42 dB. So, now look at this 34.42 is expected sound level in the receiving room. So, you see the noise criteria curve now. If the room is dedicated for any kind of the activity like studio activity, which is where you require the NC curve is 15 or 20 like that, you cannot have that kind of activities in this room, because the the level of sound expected here by transmission from 70 dB noise from the source room is 34. So, probably it may act as a machine room or some kind of a room where a laundry that you see that in NC 50s and all can be permitted. So, something like that you may permit, but something like a reading room or classroom or maybe a hospital or the other noise sensitive room, as per the NC recommendation, is not permitted in this particular area. Let us go to the next problem, where suppose there is a road, and from the middle point of the road at a distance of 15 meter there is school building, and the background noise criteria for the school building is such that there should not be any noise transmitted from the road to this school building, and that should not be more than 45 dB. So, that is number one criteria, and suppose you got a 80 dB sound at a distance 5 meter from the center of the road. The next inputs are this classroom. This is a classroom. The detail of the classroom is like this. The size is 10 meter, 6 meter by 10 meter and 3 meter is the height, and the average sound absorption coefficient alpha of all the surface is 0.3, and another input data is there is a partition wall, or there is a wall which actually there is this partition between the sensitive zone, school, and the road or the other area, outside area. It should be a wall. So, that wall has a kind of a TL value 60 dB, and there is a window is proposed also, because without window the school room and all the daylight and all, you require window for the ventilation. So, this window is, if it is closed or something like that, its TL is 15 dB. This is 15 dB TL. So, now my question is what will be the maximum area of the window such a way that this road level noise, which is 80 dB at 5 meter, should be, I mean that definitely that will go down at 15 meter, but here it should not be more than 45. Though for that, to achieve that, what is my design criteria, how much will be the size of the window. Let us proceed to for the solution. So, at the mid level, if it is some noise, and at 5 meter from the midpoint of the road is 80 dB. So, I can find out what is the LR is 80 by virtue of this equation, and I am trying to find out what is the sound intensity level at this particular point A. And the sound intensity level in this particular point A, by virtue of this equation, I found it is 10 to the power minus 4 watt per meter square. And now I go back to the road midpoint again. So, if at a distance 5 meter from this point, if the intensity is 10 to the power minus 4 watt per meter square, so what should be the actual sound source power at this particular midpoint, and I am assuming that is a spherical propagation of the sound. So, in spherical propagation of the sound, I multiply I A, that is 10 to the power minus 4 into 4 pi into this is having a, assuming this is the center of the sphere and this is the radius of the sphere as 4 pi r square. So, I can find out by using this equation the sound power at this particular source is 0.031415 watt. So, next I will find out what will be the sound intensity level at this particular point B at very near to the window or this wall. So, the sound source I know that this is 0.031 watt, and I have now found out what will be this what will be the sound intensity level at B. Again I will use this spherical equation. Now my radius is 15 meters. So, using this equation I found out the sound power level, sound intensity level is the sound intensity at this point P is 1.11 into 10 to the minus 5 watt per meter square, and by virtue of this equation I found out that sound level at B is 70.45 dB. So, 80 dB come down to 70.45 dB, but my expectation inside this particular classroom is 45. So, I have to reduce this amount of sound. So, in that the reduction required is almost 25.45 dB. Now, who will give me this reduction? How I will achieve this reduction? This reduction will be achieved in two ways. This noise reduction NR will be achieved in two ways. One, by designing this partition wall by virtue of the combination of the wall and the window, and number two is that the quality of the absorption quality of this particular inside this classroom will also give me some kind of absorption and some kind of reduction. So, the classroom size, as I told you, that 10 into 6 into 3 meter and having average coefficient of the absorption is 0.3 gives me A alpha value is 216 into 0.3 is 64.8, where 216 is the inside surface area. So, I have found out the wall area and also the ceiling and the floor area. So, with this Sabine of total absorption, I now found out what is the NR, and then this A alpha is your 64.8 and your S is your 30 meter square. So, I can write down this partition wall is this. So, write down this partition wall TL, this is 25.45 is your noise reduction, that much I have to achieve by TL plus the inside room character. So, that is 64.8 A alpha, and S is 30. How S is 30? Because this is your 10 meter by 3 meter exposed wall dimension. So, the S is 30. So, I know that this TL which comes from the transmission loss of the partition wall has to be 22.11 dB to achieve a noise reduction of 25, to get a permissible noise criteria of 45. So, now my job is, my designer's job is to create a partition wall by virtue of the wall and windows that must give me a 22.11 decibel transmission loss. So, I am now in the last part of this program, this problem, where I know the TL of wall is 60. So, that means tau of wall is 10 to the power minus 6, the window TL is 15. So, the tau of window is 10 to the power minus 1.5, and let us assume that this total the wall which is having the the partition between the outdoor and the indoor is having 30 meter square of the area. Let us assume that the window area is x. So, the wall area is 30 minus x. So, I put those values of the window tau multiply by the x, wall tau value 10 to the minus 6 multiply by the 30 minus 6 is the equivalent area of the wall divided by 30 is the total area, that means this is the total tau value, and this total tau value should be 10 to the power minus 2.211. Why 10 to the power minus 2.211? Because this is my average tau value, average TL value that I am looking for. So, I am going to found out the x value by virtue of this complex equation, and if you solve this equation, it is required a calculator only. The solving this equation is the first order linear equation of x, and you will get the x is 5.09. So, finally, I decided that the window area should be maximum 5 meter square. If you go for more than 5 meter square, your TL value is reduced down, and by virtue of reduction in the TL value, in your school building should have a more than 45 dB of the sound exposure, which is not satisfying criteria as per the noise criteria curve. So, that is the end of it, and we have some homework for you. So, let us write down and outline the relation among the noise criteria, sound transmission loss and the noise reduction. That is number 1. And the number 2 is that if the total sound absorption in a particular receiving room gets doubled, sound absorption is get double, then what will be the change in the noise reduction, assuming the other parameter remain unchanged. That means, the total surface area of the partition wall is remain unchanged, the total TL value of the partition wall is remain unchanged, only the changes occurred is in the receiving room, the character of the receiving room is going to change by virtue of the absorption or materials or so, and it gets double. So, what will be the significant change in the noise reduction level? So, that is the end of the lecture number 32. I have referred those books for this particular lecture. Thank you very much.